Good afternoon. Today I will talk about our ITSC paper, a dynamic points removal benchmark in point cloud maps. Point clouds are widely used in robotics, given their effectiveness in facility key components such as localization and path planning. Current SLAM package fuse the data from multiple sensors to obtain a corresponding pose and use this pose to integrate point cloud frames into a global map, as shown here. You must also notice that there are some yellow labeled points that are dynamic points. Those points are moving when we collect data to build map normally, and we call them ghost points. In localization task, those points may reduce robustness as they introduce ambiguous features and misleading the matching process between the current observation and the global map. For global path planning, the percent of the ghost points can lead to suboptimal path selection. If the planning algorithm interprets points corresponding to dynamic as part of static environment structure, it will mistake these points as obstacles and classify the region as untravelable, resulting in unnecessary long path allocations or even failing in the path planning. Many methods are proposed to remove dynamic points in the map. Based on our benchmark result, we summarize the strengths and weakness of each technique, reviews from our proposed matrix facilitates further development and innovation in the field. And the most important show how we could improve one of the methods through our benchmark. Except methods, our contribution also includes metrics, since there are different metrics that tolerate to showcase the benefits of different approach by utilizing the voxel-wise perception rate to evaluate their result. However, as shown here, voxel lies the ground truth map will negate the classification accuracy in the sub-voxel scales. We adopt a set of new metrics for point-wise evaluation with a unified standard. And the dataset to evaluate our benchmarking performance is also important. Existing methods are only evaluated on KT, which solely includes small town scenarios by a single type of LiDAR. Our benchmark performs evaluation on various datasets to analyze the robustness towards different scenarios and the sensor setup. The latest Algoverse 2 datasets that contains various streetscapes in the big city and have more dynamic objects compared to Kitty. A same indoor scenario where dynamic object close to the static structure and the Eagle agent is equipped with a sparse LiDAR, which is 16 channel. This diverse datasets enables a comprehensive assessment of the existing technologies to compare their adaptabilities to a range of scenarios and sensor configuration. Here are some methods pipeline in our benchmark. Removers and erasers are offline methods that require a prior raw map to compare the difference between the query and raw. Removers convert the point cloud to the depth range image and use the image difference, where erasers voxelize to volumes and use height difference between them. The occupancy mapping approach, OctoMap, is also frequently used as a dynamic point removal baseline. However, it itself is not designed for dynamic points removal task. Guided by our benchmark result, we demonstrate how we improve its dynamic points performance by incorporating with the noise filtering and ground fittings into the pipeline as shown here. Now it's the time for experiments. First, it's about matrix we proposed. The map clean task aim for two goals. Remove true dynamic and keep true static points. This process involves maintaining high recurrence in classification of both dynamic and static, often referenced as dynamic accuracy and static accuracy, respectively. Additionally, we utilize the associated accuracy calculated using the geometric means as a comprehensive matrix that combines both accuracy, offering overall assignment of the algorithm performance. All metrics are point level. And here is the summarized tables of method performance on different datasets. Removers mostly retain the complex completes a static map as shown here, 99% almost, but label only a few correct dynamic points, which means it didn't remove the dynamic points in the map successfully most of the time. Eraser perform better in removing dynamic points and balance the static and the dynamic points. The original Octomap suffer from the angle problem in the ground plane and noise points, which caused their scores on static accuracy is to be lower than others. Here, Octomap with ground then denotes the method with ground estimations, resulting in higher scores across in most of the sequence. With noise feature, the scores also higher than original in most cases. And Octomap with GF, we achieve 20 to 30% speed up as shown here, since the noise points do not undergo the recasting process. For further analysis, we illustrate where the error typically occur. We observe that most of the false negative points, which is true dynamic points, labeled as static, close to the true positive points, which is correctly labeled dynamic points. With all methods, false negative points ranging from 10 centimeters to 13 centimeters away from the true positive points. In such case, other techniques such as clustering around the true positive points can be employed to address this issue. Comparisons with improved Octomap version in E here demonstrates the significant improvement in error reductions for ground points. By cooperating ground estimation, most of the ground points are preserved, ensuring a more accuracy representation of the static environment. As these points are considered definitely static, recasting is not performed to remove ground points, further enhance the accuracy of the map. As shown in the original Octomap exhibit here, the sparse LiDAR ground point problem leading to many ground points being removed regularly by LiDAR rains. Well, Octomap with GF solved this problem. You may notice there is still some room for fine-tune our pipelines parameters like occupancy probability value, as people standing in the same place for extended periods, making it challenging to remove them using the single default parameters. And that's all. Thank you very much. Check our codes and other papers in our GitHub repo. Stay tuned with us.